I'm recording this session to be used for your online reference or review only for this class and only for students of this class. If you have problem, if you have any issue with recording this class, please let me know. Otherwise, I'm assuming that everyone is okay with recording the session and sharing it online for students of this class. Last week, we started talking about dynamics of the robots. Similar to what we did before, we limited our discussion to a very simple case. A two-linked robot with very simple structure, two rotational joints, as you can see in this figure. We have one joint here connecting to the base, another joint here between two links. And to model dynamic of this robot, which means when we talk about dynamic, we should be, discussing the relationship between speed, velocity, acceleration, forces, torques, probably mass, and all those mechanical concepts inside our robot which are related to movement, to dynamic of the robot, to the behavior of the robot. When it moves, when it leaves something, when it applies force, and when it accelerates, when it goes from point A to point B, following some instructions by applied torque, those details related to dynamic of the robot. In this simple case, to model our robot, we make some further assumptions. Okay, these further assumptions will help us to simplify equations, to write equations in a way which we can understand and we handle easily. I'm just repeating what I said last week, just to refresh everyone's mind, including myself, that where were we and what we want to do. The simplified model was we consider a point mass, means a mass which is concentrated in one point, in just in a location in the middle of each link, with link 1 mass located at the center of the link 1 with total value of m1, and mass for the second arm or second link is concentrated in the center of the link with total mass m2. All right, and we know that from basic physics, from Newton laws, that when a force is applied to a mass of m1 and it's accelerated with a1, there is a relationship like what you see here. F1 is m1 times a1. Simple linear Newton law. Okay, so in linear world, in linear mechanics, in linear physics, the relationship between force and acceleration is ma equal to f. Okay, and we saw and we reviewed that again. In rotational movement, it becomes slightly different. We have some extra components. Okay. Well, before I go again, I'm just reviewing, trying to make sure that everyone is on the same page. When we are making this assumption, we also have to make assumption regarding the location of the masses which we are using here. The location of mass m1 at the center of the link 1 here, represented by a vector called r1. Okay, when we have this r1, which can be represented with the angle theta 1, you see is related to angle theta 1, and its length is half of the total L. So for r1, which is a vector with a length of L over 2, an angle of theta 1. Also can represent that in this way. Just this vector represented by a length, which is half of the first link, and an angle, which is theta 1. All right. For second mass, we use another vector. Well, I'm repeating that probably because we got feedback of higher level of complexity in the end of the session last week. Most of the class thought that in terms of complexity, this one is higher compared with what we have said before. I also had comment from one of you saying this is probably the most difficult course I had before. Okay, so I'm repeating to show that it's nothing very complicated. We still need to think, we still need focus to understand it, but it's not that complicated. So this vector, if I call it R, okay, now this R has an angle. Look at this. So when you have, see, if you were looking at this angle, you see this vector? The angle here is, I know that this angle is theta 1, exactly same thing as I have here, right? Basic geometry. And this angle is theta 2. So for R2, I call this R2. For R2, this is R1, sorry. So for R2, I know the length is, this one was L1, this one is L2 over 2 with the angle of theta 1 plus theta 2. And our new R, pointing from center to the mass at the center of second R, okay, based on vector analysis, basic vector analysis, if this one is R1, this total longer one will be 2R1. So R will be 2R1 plus R2. Then we can combine these two vectors together to find the new vector, pointing to the second mass at the second link of our product. Okay, just step by again, redoing what we did last week. So acceleration of the first link is represented by the second derivative of the location. So your location is R1, second derivative of location will give you acceleration of the one. And acceleration for the second link, for the first link, sorry if I said, I don't know. For the first link, acceleration is R1, second derivative. This is second derivative of R2. So not in this way, but second derivative of R1. And this is second derivative of R, location of the second mass, which is R, will be this, because we know that R is equal to 2R1 plus R2. That's why we are getting this. Okay. Basic vector, a basic Newton law. We combine these two together to have a better understanding of movement of the robot. Any question to this point? So this part is super easy, right? The relationship between mass location and the acceleration of the robot. Now we need to consider the rotation component, so because what we have in our robot here is not a linear movement. It's not just simply a linear movement. What we have is having here rotation, because this point is fixed, and also we have another rotation. And, well, this rotation will be combined together, right? So, and we have to just consider other components. When we have a rotational movement, you have a arm moving fixed at one side and the other side moves, right? There are two components of acceleration. One component is tangential, which is talking about one which is tangent of this movement at the end. So when I have a movement, let's have it here. Okay, one is an acceleration which you have in the direction of tangential, means there's just touching end of the vector, whatever vector it is, r or r capital or whatever vector it is. Okay, like our case, which was r, tangential. Okay, a t, and the other one is radial or centrifugal, means that an acceleration which tries to keep this on a circle. Because if it wasn't this acceleration, if it wasn't this force coming from when you have a rope connected to a weight and you're turning that, there's a force through the rope to the item or through the link to the mass you are rotating. So we have an AR in this direction. The value of the AR is related to the speed, rotational speed, and the length of the link. Okay, and while we know that omega is rotational speed, is the first derivative of the angle. Rotational speed is the first derivative of the angle. Sorry, just like that. First derivative of the angle, the omega. And it's negative because it's onward, it's coming to the center. It is trying to keep the mass on a circle, so applies a force toward the center of the coordination system, the center of the rotation. Okay, center of the rotation. Tangential, on the other hand, is just touching the circle. If you have a circle like this, it's a tangent of the circle at each point. Okay, here, like this. All right, so we have two accelerations in mechanics of the robot. And it's not just robot. Wherever you have a rotation in the system, a mechanical system, you have to consider rotational components. Speed, instead of position, we talk about angle. Instead of velocity, normal velocity, we talk about rotational velocity or speed. And instead of acceleration, we talk about rotational acceleration. All right. And well, same thing as you can see here is shown. So this gives me a hint about what we need to do as a second derivative of our components, our mass components in the robot. Our mass components in the robot. Okay. So second derivative of R will be rotational acceleration of the mass of the robot link is related to the omega to the 2 and alpha times R1 and omega and alpha times 2 for the second one. So for individual links, for each link individually, we have this, right? We have this. And this alpha is rotational acceleration, which is second derivative of theta. So what we find is if you want to translate rotational movement into linear, if you want to explain rotational movement, you have to consider both. Rotational acceleration, and also you have to consider the speed for the force you have toward the center of the mass, to the center of the rotation, not center of the mass, sorry, center of rotation. So second derivative of R1 and R2 will be theta 1 to the power of 2, theta 1 dot to the power of 2, which is omega. This is omega, and this is your alpha, omega 1, alpha 1. for the mass number 1. So what I have is, now there was a mass here, M1. There was a mass here, M2. For this one, I had R1. For this one, I had R2. Still, I'm not talking about R, the final R, just individual R's, okay? I know that movement of this one is in the angle of theta, okay, theta 1. So this theta 1, the movement, the rotation here rotates around its own center, and this one rotates around its own center, okay? Individually, if I just consider them as two independent movement, acceleration of R1 will be represented as this, and acceleration for R2 will be represented as this. And K here, K is the vector coming out of the plane, coming out of the, so you know that this is I, this is J, and this is, sorry, this is K vectors, okay? And we have a cross multiplication to show the direction of this movement. So you see it's coming up and R is going out. External multiplication will give me this direction, This is K external cross to R. The direction of this vector can be found by external multiple cross multiplication, cross vector multiplication, because we say inner product and external product, but this cross multiplication gives me the direction of the acceleration in that. Okay, so what we have can be concluded here. So for each link of my robot, I have acceleration independently calculated, and we have theta 1, theta 2, and what we have here is acceleration for each mass. See, here is the center of M1, M2. So what we have here for this one and for this one, acceleration of this one is defined by R1. Acceleration of this one is defined by R2. Okay, by R2. All right. Any questions so far? These are just basic vector calculation. We don't need further more than this. We just need to have an understanding when I have two objects connected, linked together, and they're moving. There are angles and vectors to be used in our calculation. No question? Very good. Going back to the force. Force was, again, mass multiplied by acceleration for both links, F1 and F2. On the other hand, we know that torque, which is, so again, if I use this structure, I have a mass here at the center. I have a mass here at the center of the other one, M1, M2. I'm talking about the force F1, force F2, whatever direction it is, okay? Torque here will be the torque you're applying to the joint number 1, tau 1, and joint number 2 as tau 2. The torques we are applying. For, you're applying here. Okay, so well, I have to be well, to calculate this, I have to consider this vector f times r times f, the vector I have times f, to give me the torque. And for the second one, since I had, this length, again will be r, long r, multiplied by f, which gives me this torque times m2 a2. Okay, a2. If you calculate the total torque of the system, total torque of the system, you see the relationship between force, mass, acceleration, and torque. By replacing what we have here for A and R, what we get is for torque number 1, we get m1 r1 second derivative of theta, direction of k. And for second tau, we have acceleration times force times length, as we had here, 2r1 plus r2 times m2 a2. For this one was was r1 times f, which was r1 times m a1 vector. And to simplify that, when we have a couple of vectors multiplied together, we use some mathematical manipulation. The important thing for us is just to understand that torque 1 is related to r1, theta 1, and m1. And torque at the second mass is related to the first angle, second derivative, second angle, second derivative, and speed of first link and second link, and speed of the second link as well, plus the length and angles of the robot arms. So if I look at that, well, if I look at this, what I have as torque, what I have as torque is a relationship which makes sense, relationship between what I have with m, with r1, and with theta 1. And also torque 2, the torque I need for the second one is related to m1, is, related to m2, related to m2, related to theta 1, related to theta 2, related to r1, and related to r2 as well. The torque I need, okay, for the second one. And on the other hand, we may consider our two-segment robot consisting of 2-point mass of 2 massless rods. We did that. As a consequence, Newton's law will be, Newton's third law will be action. There is an equal opposite action. We have a theorem stating that the torque in a system cancel out so that only torque of the external force are relevant. Which means that when you're applying force to this robot, what is important in your movement in the final arm is what you're applying in the total torque is to one which you have at the base, which you have at the base. The torque of the external force on our robot system are the torque of the gravity, okay, because of the mass of the objects, and torque exerted to the base on which the robot stands, the one which is connected to ground, which is connected to an independent center of movement, which is ground. You don't move that, so your robot arm, the torque will be applied to the robot. Because what you apply at the second one, when you have your robot at the second link, what you apply here, opposite of that will be applied to the other one. So these two will cancel each other because this is part of your system. It also moves. So when you have a robot arm movement, So the other one will cancel out the what you are applying to the second. Okay. So the torque acceleration, the torque of the base is equal to m1 and the actuator in the first point. The sum of the torque and the external base and gravity will be totally equal to theta 1 and theta 2. So it tells me that the torque my motor needs to apply is the total torque you're applying to the system, which will be m1. Sum of the torques produced at the external force coming from outside is what you have m1, and the mass, or actually the gravity force exerted to your mass, to the mass of the robot itself and the load which it carries. So if I well, in the angular form, if we do the calculation, what we will get simply is, so I just go to the final one to explain it. It might be much simpler. So total torque in the system is theta 1 plus theta 2 on one hand, and the torque applied by your motor plus the torque you have because of the gravity. Again, by replacing this R1 with this R1 plus R2, simplifying this, so M1, and moving this part to the other side, the motor torque, what you need to produce at the motor of your first joint will be equal to the tau 1 plus tau 2 minus R1 M1G because of the gravity and because of the gravity of the second mass. If I replace everything, it gives me this long, scary equation. Okay, this long equation. The torque you need to produce at your motor, it would be calculated based on acceleration you're applying to the first robot arm. The acceleration you're applying to the first robot arm. If I have these two again, the acceleration I have here, so this is theta 1, the acceleration I have here, multiply this, plus acceleration you have at the second one, okay, and multiplication of the speed of 1 and 2, and the second, well, to the power of 2 square of the second angle speed, rotational speed, and also gravity effect on your system, So if I rewrite and expand this to have a better understanding of what we have. So here, C means cosine, and S means sine, as what we had before, sine and cosine. Okay, so what components you have in your motor torque calculation? This is the more important result I'm looking for. One is inertial. Why inertial? Because it's related to mass and acceleration. It's very similar to what we had at linear mechanics, linear dynamics. Very similar to what we had at linear dynamics. Mass acceleration. So this is similar to that. We call it inertial movement. This is here because to move a mass sitting somewhere, when I have a mass which is not moving, is sitting somewhere without any acceleration in movement, I want to push it, when I want to make it move, I need some force. I need to apply some external force. It's not because of gravity. It's not because of friction. It's not because of any other thing. It's because I have a mass, and this mass wants to stay in its position. It's mechanic, right? And when you want to move it, you have some force. So this is inertial. Heavier your robot arm, heavier your load, more this inertial will be. And faster you want to drive it faster, you want to move it, it will become more. Okay. Inertial coupling. This is because of the second mass connected. Because at the first arm here, we have to, well, this motor here at the base, this motor at the base, it applies a torque here. One thing is moving this mass, and the other thing is also moving mass 2. Both are loads connected to the first motor. And that makes sense. When I have a robot arm, the robot arm base is sitting on the base, but when it moves, it has to move all the connections or the links to the end effector. So this is also inertial, but inertial because of the second one. So we have these two. We have two other components. The other one is centrifugal. Again, similar to what I said, since this is a rotational movement, we have an R junction here, joint here, and we have an R joint here. Well, specifically this one, when it's moving, because these are moving on a circle, you have a centrifugal, you need centrifugal force, which is translated to torque here for us. Is multiplication of speed of the 1 and 2 and speed of the second one to the 2. So it's related to the speed of both this mass and the other mass, and also related to the mass of this that we have. Okay, the mass of the object we are moving. And the third component is the gravitational. Because of the gravity. This is because of the gravity. This is well, mg, you know, that 9.8 Newton. So per well, you have this mass times g L1 because L because of the length and L because of the length of the object, and cosine. So that this should be L1 and this one, the other one should be L. Just the length of R1, okay, related to R1, and R2 is L over 2. Okay, everything is, well, with these assumptions. We have R1 and R2 related together. So 4 components in our torque: inertial coupling, centrifugal, and gravitational. That's the point you need to remember when you're talking about dynamic of the robot. And torque of the second joint, or the motor you need to use in the second joint. The torque which it produces is R2F2, again similarly, which will be components of, well, different acceleration and speed effects. One is speed, related to speed, and related to acceleration, and while the component at the end will be m2 divided by m2. The mass of the second one is speed, acceleration of both, and dislocation of them. Relate that to the gravity. So this one is for gravity. This one is for inertial. This one is for inertial coupling, these two, and this one is for the other component we had, which was centrifugal movement of the robot arm. Okay, if I simplify that by assumption of R1 equal to L, R2 equal to L over 2, half of that, you can simplify this, the components, as you can see here in the dynamic, which again is inertial coupling between 1 and 2, inertial, centrifugal, and gravitational movement of the objects. Any questions so far? No question?
So I have a question here. So basically the torque is meant
Find the
to
relationship
take
of
the
torque of the
initial.
motors of a robot on your arm. Can you do that? Without looking into slides. Yes or no?
One slide.
I need answers.
Can you?
Goran, your answer is yes? Okay, it seems that no one is listening. Okay, Jason, thank you. I don't think you are getting us stuck. So I didn't hear anyone. Oh, sorry. Okay, yeah. All right. So did you say anything, Jason? Sorry, I didn't hear anyone.
Can you hear us now?
Oh, yes. So sorry if.
Yeah, we had talking. Borhan had questions and stuff.
Seriously? Oh, I'm sorry.
Yeah,
I could
Nassim.
silent. I was upset. Okay, so you can. No, I didn't hear any question. I'm sorry, Gor. Okay, you didn't hear my question. My question was, I have been speaking, Jason. Okay, my connection.
We have been hearing you talk, but when we try and ask you a question, I don't think you've been
No,
hearing us
it was
responding.
sorry. It was my system. The speaker was very low. I couldn't hear what you're saying. Did I miss anything or any question you had from me? I'm sorry about that.
Question on this when you're talking about the torque, the second one where you have M2. So are you just replacing in the one where M2 over the lower case M2, just replacing with variables we already?
Step by step. Go. You're talking about here the M2, or do you remember which slide it was?
The slide we are seeing is the one that shows torque in the second joint.
Okay, torque in the second joint. So not this one, right? Here.
Yes, that one. So the slide you were on. Yeah, I'm just trying to go through and follow which variable they're changing for where when you're showing the last formula.
Okay, all right. Here, this one. From this to the last one, right?
Yes. There
From
we go.
this one to the last one. Okay. From this one. So is this one clear what we did here?
Yeah, I understand the R2
Okay,
and then
very
the
good. So
R2
here,
second derivative.
exactly. So here, what we did is, well, this is basic torque calculation. This is basic torque calculation. And it's not just for robot. Whenever you have a joint and you have a mass connected, or you have an object applied force here, creates a torque. You can convert that force to torque or torque to force by just looking into the length you have here. So multiplication of this R with F gives you the torque, considering them, both of them, as vectors. Okay, so this is a vector multiplication. And when I replace that, so you see, to replace that, I replace my force with this. My force with this. Well, not with all of it, but you see R2, 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 really, because my force are, I have three components in my force. One is acceleration, length, because I have two R1 and R2 connected. Okay, R1 and R2 connected. So I have this, and gravity components. When I replace them with the values which we had before, what I get here in this equation is just replacing these with these components. As you can see, this and R2, this is a scalar. You can take it out, okay? And we'll bring it back to the calculation. And same thing here. This one is scalar. This one is scalar. So you can make it like product between vectors. These vectors can be just R vector or derivatives of the vectors. Okay, so that's why we have here theta 1, R2, and R1 and R1, you know, just replacing them like what we did before based on what we had before, we will get this equation. Okay, and from here, we can just, what we did was the same, similar thing, because I know that when I have external product like this, or cross product, sorry, just sometimes you call external, but cross production of two vectors, the value of this cross product, A times B, the absolute value is A times B times sine of angle between A and B, like what you have. Angle between A and B. So for instance, when I'm doing this, the angle between R1 and R2, this was R2, this is R1. So the angle between these two, this one was theta 1, this one was theta 2. So angle between them is theta 2. If I continue, so sorry, if I like this, theta 2. The angle is theta 2. That's why when I multiply these two will be just size of L1 times size of R1, size of R2 with the sine of angle theta 2. Size of angle theta 2. That's why you see theta 2 here. R1 times R2 theta 2. And same thing goes with others. Well, when you replace, when you look into the angles of these components. And if I rearrange everything, I'm getting this relationship between components. How do I rearrange that? Based on what is multiplied to the others, based on theta and theta derivatives. So all the components have theta 1 derivatives. I take them out like this one, like this one. See, are coming out as theta 1 second derivatives. I just replace them with these assumptions, You see they are coming out as different components shown here. Okay, so what I have is R1 times R2 cosine of theta 2, and which gives me L times L to the 2 cosine of theta 2, which is this one. And here R2, which is L over 2 to the power of 2, makes it L2 over 4, which is this one. Okay. And well, and the rest of them as well. You rearrange them based on what you have. And the result will be similar to what we had before. 4 components: inertial coupling, centrifugal, and gravitational components. Okay.
Perfect. Thank you.
Thank you for the question. And sorry again, I missed what you said in class. So any other question? Couldn't hear the question. Okay. So any questions so far? All right. So before I continue, I want to know, can you redo what I did without using the slides? So let's say you're not doing that. I want to see what is the level of understanding in class. Just so can you redo what we did? Means finding the torque you need at motor 1 and torque you need at motor 2 without looking into slides? Yes or no?
No.
Lou says no. So I have two no. Three heart. All right. Okay, Jude. Okay. Elton. Nope. Yeah. So means rest of the class can do it? I don't think so. All right. So no one can do it. So what if I let you to look into the slides? So if you have the slides, and well, just to help you to do it, I'm not saying just copy and paste. What if you have slides in hand? Also go through and look at it, and what do you think? How do you rate this in terms of difficulty from 0 to 10? Difficulty level. For me is, well, no, I won't bias anything. So
Around a 9.
9, so enter it, I can read. I won't be able to do it efficiently. 9, okay, or 9. Milton 8. Jason 9. Okay. Jude 8. Good. 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 Well, similar to what we had. 9.5. I'm wondering what is that 0.5 coming from, Nasreen? With YouTube, maybe 10. With YouTube. Okay, so yeah, there are good videos on YouTube as well. But see, the basic thing is here. Just before I move forward, I know that well, in the type of test and exam we have, it wouldn't be possible to ask you to prove anything. I just want to make sure we get the understanding. Two things here. One is the ability to write the equation. That's one level of capability. The other one is understanding. Well, understanding, we do understand mechanic by nature, right? I know when something is heavier, it's more difficult to lift it. I need more torque. I know if my robot arm is longer, I definitely need a stronger motor, right? These are basic understanding. We do have that. We do have that, okay? But for the calculation, very fast from what I did at the beginning. I don't want to go here. I need space. Very, very brief on what we did. Okay. What we did was I had a structure, okay, with mass M1 and M2. If you want to explain that to someone just briefly to say how do we do that, okay, what we did was we have one vector R1, we have another vector R2, and we defined a third vector R, which was we had R1, M1, R2, M2, right? And we also define R as R1 plus 2, I'm sorry, 2R1 plus R2, okay? So this was the initial point. This was the, well, starting point, and we know that we have theta 1 here, and we have theta 2 here, okay? What we did basically was first finding accelerations and relate accelerations to thetas, angle and length of the robot. So we had to build up that relationship. Then we made this FMA, and then we create this. Well, whatever R, this R is not that R, so I'd write it like a capital R, okay? Capital R. These are vectors. Okay, these are vectors. So what we did in this part of the calculation was basically on these steps. So I had to define my vectors. Then I had to figure out what is the relationship between acceleration, angle, and r. R means length. Okay, r just length of distance of the mass from center. Distance of the mass from center. And here I had to understand rotation or rotational movement. That was a major point. I had to understand the rotational movement. And here when I had this, so when I had this, just having ma gives me the relationship between acceleration and force. I have force by using again distance from center and vector cross multiplication. I can find this torque. I can find torque at each joint. Then we just added all torques together to find out how much torque we need in our motor. Okay, so considering torque effect of each mass independently, then combine them together as a whole system to find how much torque I need to be applied by my motor 1 and motor 2. Okay, these are just basic points based on which we just did the calculation step by step to get to these equations. I understand it is long. I understand it might sound difficult, but this is just one time exercise we need to have for robotic. It's the simplest calculation I could fit in. This can be extended to other type of calculations, just larger kind of calculations. But we are not going in that direction. But for it, this is the minimum one. When you pass a robotic class, you should be familiar with. No one expects you to be able to just do it without thinking or without just reviewing what we did in the class. You need to definitely review that. I need to review everything if I want to redo it. But you need to have seen this. You need to be able to understand that and explain that step by step. And probably one of the major take-homes for this is what defines or what determines my required torque, because this gives me what kind of motor I need. This is a torque of the motor. And for those who had class of energy conversion last semester, or those of you who will have, we have a course called energy conversion in which instructor will talk about different type of motors and torques you produce and relationship of that torque to the input current or input voltage or the structure of the motor. All those details, while here can be used to to figure out what type of motor, what size of motor, how much current or electrical energy I need to apply to my robot for this movement. Okay, so that's the beauty of the work we did. That's the beauty of the work, because now we can make a relationship between on how much energy, how much torque, how much in terms of size and price I need to spend on my motor for a specific type of robot. If my robot is 2-link, if the first link is L and the second link is half of it, so the robot we're talking about here is something like this. So this one is L over 2 and L over 2 and R1 and R2. So the size are, so these sizes, right? Just consider L1 and L2. Also relates to M, linearly M. So everywhere you see M1 and M2, they might have been multiplied to different numbers. but you have M1 and M2 at different locations. Also, it is related to the acceleration. It's related to the angle, which makes sense, right? At different angles, you might need different torques because, well, effective length will be affected, will change with different angle between robot arms. You know, higher or lower makes it different in terms of distance from the center. Okay, angle itself as well. You also need to look into the acceleration of the second link, and well, length as well, and speeds, and also you have mass again, length, and gravity are well, gravity is a fixed value, so you have also again angles and gravity and mass components in calculation of your first motor required torque. For the second motor, when you look at what you have here, again, you see mass 2, mass 2, mass 2, mass 2, mass 2. Right? Because this is the second motor connected to the second link. You don't have mass 1 here because mass 1 is, well, sort of base for the second one. So here we're talking about the, we're talking about the torque I need here. So that makes sense that I don't see mass 1 because mass 1 is out of scope. I only have mass 2 for this calculation. Mass 2, right? So I have mass 2, an angle 2, an angle 2, and an angle 2. I don't see any. So this is cosine of theta 2, sine of theta 2, cosine of theta 1 plus theta 2. Why I have cosine of theta 1 plus 2? Because of the gravity. Because, well, these angles both together defines the height of the or the movement of the mass of the second link. That's why I have theta 1. So if I ask you, does well, mass of the first link have any effect on the torque you need at the second link? The answer is no. I don't see any mass 1. Okay, but if I ask you, like the test, is there well, does theta 1 has any effect on the torque you need at the second link of a 2-link robot? The answer is yes or no.
Yes.
Yes, answer is yes. And
it's only for gravitational though, right?
Thank you. Exactly. So, and only on this part. So if you have 5 answers, it says yes because it affects the inertial movement of the second link. Or no, it doesn't have any effect. Or yes, because it affects the centrifugal component of the torque. You see, no. In centrifugal, I don't have theta 1. Here, I don't have theta 1. So not in this one, but I have it here. Yes, because it affects the gravitational component of the second torque. So that's what I expect from you. So in the test, you should be able to give me, you know, a sort of analysis, sort of understanding on this, right? So sort of question, what I do, I'll look at this and try to create questions based on understanding of these different components, okay? I don't expect you to write them. Well, I expect you to be able to do it. Honestly speaking, I expect you to be able to do it, but it doesn't mean that I want you, well, I'll give you limited time to do the calculation, well, to drive the equation. Happen is fine. If I give you M1, L1, theta 1, speed, gravity, if I give you different components, ask you what is the inertial component of this torque at motor 1, you should be able to calculate that, right? Because you have the equation. If I give you the value of M1, if I give you the value of L, R1 and R2, if I give you the value of M2, if I give you the angle, and if I give you the rotational acceleration, the alpha, theta 1, you should be able to calculate that. This is one equation. I expect you to be able to do that. I expect you to understand this as well in terms of calculation or in terms of explanation. Tell me if you see any, does, for example, does theta 2 has any effect on the inertial component of the torque for motor 1 in the two-link robot? The answer is yes, because I see a cosine of theta 2 here. Cosine of theta 2. This cosine of theta 2 is kind of inertial added to my original link, because while I have this and this load is there. So the torque I need to apply is to apply this one to to overcome force here, and also needs to move this one as well. This one is also connected to the first motor, and so on and so forth. Endless number of different questions can come out of this. You need to have an understanding of this.
So cos C2 is cos theta 2.
Yes.
And
Similar to what we
C
have.
is cos theta 1 plus theta 2.
Exactly.
Okay.
Okay, so for your reference, C1 is cosine of theta 1, S1 is sine of theta 1, C2 is cosine of theta 2, S2 is sine of theta 2, C1 is cosine of theta 1 plus theta 2, and S12 is sine of theta 1 plus theta 2.
Yeah, thank you.
Good thing. Is it difficult now? It's still difficult.
On your slides for the first joint and the second joint, one says inertial and inertial coupling, and then the other one says inertial coupling, then inertial.
Oh, okay. Inertial coupling.
They're swapped
And the
on
other
the
one
second
is
joint.
in order, right?
Yeah.
Are those good?
Yeah, this one, we have it because they're connected, right? Yes. Because the first one is connected to the second one. And, well, how did I figure that out? It's a connection, because here I'm talking about the torque at motor 1, at joint 1, right? But I see second derivative of the angle 2, which is related to link 2, right? So this is because I have a coupling between these two, right? Well, on the other one, I hope, yep, here. You see, talking about torque at motor 2. So when I have second derivative of theta 2, it's inertial. So this motor is affected by inertial of this one. But I also see theta 1, second derivative, which is related to the first link. To the first link. We call that inertial coupling of the 2. Inertial coupling of the 1 over 2. That's the reason, you see? Well, the order doesn't matter. Order doesn't matter. You have to look at it. So you're talking about link 2. So theta 2 is something of itself, right? Theta 2, you have a mass. And that's the inertial of that mass. But you also see theta 1, second derivative, which is inertia for mass number 1. This is because these two are linked together. These are coupled together. Does it make sense now? Is it better now? Yes. Okay, good. Very good. So any question so far? All right. So now you understand that what is my expectation as well, right? So my expectation is just understanding the final equation, also understanding how did we get there? How did we get there? While memorizing, it doesn't need memorizing. It just need practice to go. And I'll give you assignment is just to do it again. Please try to do it again. You need this understanding. You need this. You have to at learning curve of doing this calculation. Honestly speaking, I'm repeating myself. I know that I did my best to make it with minimum a load of required previous math. Okay, I normally in a class when we are sure that students have enough vector algebra, that enough matrix background, they have enough everything, so go ahead and students should be able to do it. But for your class, I understand that we have different people at different level with different background, so I don't expect you to do everything like memorizing everything, but understanding is something which is quite fair for us. And when you get your degree, you can be proud that you can explain that at least. Okay. Any question? So now what I'm going to do is I have two equations. I have two relationships between M1 and M2 and angles. Okay, so let me go to the other one. On one side, I have M1 and M2, means the torques I need, I have to apply through my motor 1 and motor 2 to link 1 and link 2. And on the other hand, on the other side, I have two variables here. In these robots, I have only two things which can change, theta 1 and theta 2. So relationship between these. When I look at these equations for M1 and M2, I see a pattern of components between M1, M2, and theta 1 and theta 2 in the calculation. I'm trying to reorganize that. I'm trying to make it more straight just by looking at the equation. So I'm going to use matrix representations for that. Okay, matrix representations for that. I define a matrix. We call it torque matrix. Is M1 and A2 vector actually. This is a vector. Two rows, and that I have only two joints, so M1 and M2. This is my theta matrix. I have Q, which are quantities we control. I have control. I read theta 1 and theta 2. Okay, theta 1 and theta 2 I define as Q. First derivative of theta 1 and theta 2. This is a vector of rotational speeds. Actually, omega 1, omega 2. You can also call it. And the second derivative of angle 1 and angle 2, which you also can call them alpha 1 and alpha 2, just rotational acceleration for each joint, okay? Derivative of it. So a relationship between theta, between tau, q, q dot, and q sec, all right? So the relationship ideally should be something like a matrix B times second derivative, a matrix C times second derivative, and G times a G just as a constant. Okay, so this will be like very similar. Look, this should remind me something like this. This is in linear mechanics. In linear mechanics, if I have an equation such as if I have one F equal to a second derivative of a function or a variable, like second derivative plus b first derivative plus c. It's not related, it's not the same thing, but I'm trying to create something like a second order differential equation. In linear math, in linear physics, in linear mechanics, it will be just simply numbers multiplied by first, second derivatives and a constant. In matrix world, we try to mimic that with a matrix B, which itself is a function of Q, function of angle. A matrix C, which itself is a function of angle and derivative of the angle. And a G, which is a function of angles itself. So look at what we have in terms of equations. These are our calculation results, which we did so far. These are our, so this can be part of your B11, which you see this. And we try to isolate different components of those matrices. And this one is B21 and B22. Okay, so if I write it down, as you can see here, B was the component, BQ was a component times Q second derivative. Okay, second derivative. So that's why I was looking for second derivative, second derivative, second derivative, second derivative. So it will be 1 over L2, you know, this is coming from here. All right, this is coming from here. I'm not doing any further calculation. I'm just trying to rearrange everything in the matrix for in just same equation. I'm not touching anything. I'm just trying to isolate them to give them a better shape, a better appearance compared with the original one. And this one is coming from here, and this one is here. So it creates a matrix. We call this matrix B. Why BQ? Because it's a function of Q, function of angle. How do I know? Do you see any theta here? Do you see any theta in B? There's no theta. Do you see any theta in this matrix? Is there any theta? I said a function of Q theta. Is there any theta? You don't see any theta. Josh, do you see any theta? Josh? Yes. The reason I'm asking Josh because he asked me a question which is related to the answer. Look at this. Right? These are components with theta, right? This is cosine of theta 2. This is cosine of theta 2. These are cosine of thetas. That's why. So there is theta here. It's hidden in these cosine values. In this example, it's just theta 2. In this example, it's just theta 2. It could be well, different if we had a different structure of the matrix. Okay. So there is a vector like that. And also I can go for centrifugal. Centrifugal, you remember, it's related to the speed of rotation. So here, this component times V2, or this component multiplied with V2. And wherever I have speed, I can isolate those as well. So this will be my matrix. So if you remember, it was Q, function of Q and Q dot times Q dot as a matrix, times Q dot as a matrix. And well, this one is coming from here. This one is coming from here. Well, this one is coming from here. And since I don't have anything multiplied by theta 1 at well, at the at the second one, sorry, anything by theta 2, there is nothing multiplied by theta 2 dot here. There is nothing, so it will be 0. It's not related to theta 2. Listen to here. Okay, this is my matrix C, and for the gravity, I have these components of gravity here and this component of gravity here, which gives me, well, basically a compact form of the relationship between torque at the motors and angle. It's not easier, it's not different, it is same thing, but it's a compact form. Why we are looking for a compact form of this representation? For generalization. Now, here in this class, we talked about just two-link RR. If someone in more advanced robotic, here's introduction to robotic. If someone wants to do it in more advanced robotic concepts and to continue this in other courses, this is the base for other robots. For other robots, you know that there are 3 different components. One component related to second derivative, one component related to first derivative, and one component is just related to gravity. And you can build up the relationship for those based on what we learned here, okay? And also the other application is in actually in reverse dynamic, forward dynamic. Sorry, we didn't. Reverse in forward dynamic is how much. So what would be the acceleration if I know how much is my torque and my speed? You know, just the forces. If you want to do the calculation the other way around, if you want to do the other way around, you know how much torque you are applying. Now you want to find out how much is the acceleration. So in that case, you can use this matrix form, finding the inverse matrix of one of them, multiply, and well, do the calculation. It is out of scope of my class, but gives you a hint on how far it can go. If you want to do more advanced robotic in calculation, it will be based on differential equations and also vector algebra and multidimensional calculations for more advanced robots. For example, normal robots we use in industry with 6 degrees of freedom. You can imagine how are equations for that one if you want to write them down and do the calculation. And the other important achievement or other important use of this mechanism is you can represent what you see here in a block diagram like this, or this one, or the other, this one, a block diagram like this. So look what we have here. For some of you, it looks familiar. People who had a course called control systems. For many of you, might look very, just unfamiliar, or you don't know anything about this. Well, we are not going to be tested on this. I just want to give you a concept. I want to introduce you the concept. For people who had already control system, trying to connect this to what they learned over there, and for those who are going to get it in next few semesters, we don't know, depending on the plan, you keep this in mind, and over there you see some extra material discussing how to control a robot. But when I talk about control, we are talking about stability. We talk about how to make it a first order, second order. To stay away from the difficulties, make it reduce sensitivity. These details of control. These are new concepts. For those who are familiar, you'll learn it later. But the basic thing is here. Block diagram. In this block diagram, you see, well, you can represent a robot, two-link robot, like this. Two-link robot, a very simple robot. Sorry, not very clean, but a two-link robot like this, using a systematic representation as we have here. These are integration. These are integration. In Laplace domain, who are familiar with Laplace domain, they will be as -1 or 1 over s. Okay. This block diagram gives me a relationship between the input tau, torque you're applying, and the angle you get as your output. You see here, it's similar to what we had in kinematic. In kinematic, we're talking about what would be the position if I know what is the angle. Okay, we're trying to figure out where is my end effector right now. If I know that angle 1, angle 2, so on and so forth are at these values, right? Now here, based on mass, size, and other dynamical component, you can calculate your angle based on applied torque, based on the torque you are applying. So this gives me a relationship between these guys, right? So angle and torque. What is involved here are the different components are which are those matrices we had, those matrices we had before, and with integration and details. This is something like, well, starting point for more advanced robotic discussions and courses. For our class, we stop here. This is, you need to see, you need to just understand. If someone shows this to me and says, okay, you know what is this? And can you explain just basically what does it say in terms of a robotic and two-link two-arm, two-armed robot with two arm joints? Well, yes, what I have is B, C, and G. B is related to inertial, and C is related to centrifugal, and G is related to gravity, and I see that integration of different values, Well, my centrifugal is related by rotational speed. You see rotational speed, and also it's related to the angle itself. So centrifugal effect will come and will be subtracted from my initial torque, and we will apply to the system. I have gravity. Gravity has nothing to do with the speed or acceleration. It depends on the location and the position of the robot. So that's why it's only a function of theta or angle. And based on theta, and sizes and masses of my robot, I can do basic calculations to find out what is the effect of gravity at each angle, for each position, each selection of different angles of my robot. I can find gravitational force. That also will be subtracted from my force. And also, inertial as well. You can calculate that and have a relationship between your applied force and the movement of your robot, which we call it dynamic of our robot. So this is the matrix representation and block diagram of the robot, just for two-link basic robot. Any question? Okay, no question. So if you have survived this part of the course, which thanks God everyone is that while your robotic, you can do robotic. It means that your robotic is, this is probably the most difficult part. I don't think most of the students I have seen, they have the peak of the difficulty for them is the dynamic of the robots because it brings in different components in one and expects you to do calculations in vector and matrix based, and also Newton law, just rotational movement altogether. Any question? So if you agree, we stop here. I give you, well, we go for a break and come back, and I change the subject. I go to another subject. It will be parallel robots, and hopefully that one will be more, more straightforward and easier to understand. Any question for me before we leave?